Hello and welcome to the Daily Space for today, October 19th, 2018. I'm sorry for the late start today. Sometimes as a scientist, I find that I have to be cloned, and cloning doesn't quite exist yet. And in my attempt to be two places at once, I could only be one, and that made the show a bit late today. But nonetheless, I am here now, and I am here to put science in your brain. Today we have a variety of stories, some of which I gave you a brief intro to yesterday, and today we'll cover in a little bit more detail. Now I'm realizing my screen may not be lined up, so prepare for things to be a bit Picasso. Why, yes, they are. Let me fix that quickly. There we go. So in our first news story of today, this evening, if all goes well, the Bepi-Colombo mission is going to be launching from French Guiana. It is on a mission to send two little spacecraft tied together or bolted and otherwise put together in a very meaningful and secure kind of way. It's going to send these two little spacecraft on their way to a 7-year mission to Mercury. These spacecraft, built by the European Space Agency and JAXA and Japan's JAXA Space Agency, are going to be on a mission to explore Mercury in ways that it has never before been explored. One will be taking higher resolution images than we presently have, and the other is going to be exploring the magnetic field in the region around Mercury. There will be more details about this mission tonight during our live coverage of the launch event. Tune in half an hour before launch is scheduled. Follow us on Twitter for updates if the mission is delayed. Currently, I anticipate going live a little bit before 10 p.m. Eastern, which is 7 p.m. Pacific. For the rest of you, do math. Sorry, time zones. You're all over the world, and daylight savings time isn't. So we're about to have another pair of spacecraft, we hope. As always, don't count your spacecraft until the data returns healthy. Moving on to a case of healthy data, I have a tale that I highlighted yesterday of a comet with a single component, not so much tail, but outburst of material around it. This object has the rather unpoetic name of comet. I'm going to say this wrong again. Please bear with me. A comet named Sack-Weismann-Wachmann 1 29P. This object is a rare kind of comet referred to as a centaur object. This is a comet that is in a highly unusual circular orbit. It was observed in great detail, and in following this object along its orbit and observing it in its evolution, it was observed to have an outburst of material. This is something that is not unusual for a comet, but what was quite odd was that the material that surrounded it, that layer of dust and other stuff that reflected light back to us, didn't have the standard composition of many different kinds of atoms and molecules. Instead, it seemed to be made of a consistent kind of dust, a magnesium-rich silicate that appeared to have small amounts of iron. For instance, this is chemically called an iron-magnesium silicate. This isn't the kind of thing that we're used to seeing. We've seen single composition comas around nucleus before, but the one time that happened was with the comet 17P Holmes. But in that case, the outbursts were made of carbon monoxide and carbon dioxide, things that we're totally used to seeing in comets. Well, magnesium, iron, silicons aren't unusual. It's just weird that that's the only thing that we're seeing in the coma around this nucleus. So here we have a weird comet in a weirdly circular orbit with a weirdly single component nucleus. This is a weird object, which scientifically makes it extraordinarily awesome. And since it's on a circular orbit, we can just keep observing it. It's not going to escape the ability of our telescopes to see by moving on an elliptical orbit out to the far nether regions of our solar system. So keep your eye on, and here I go trying to say it again, keep your eye on Sac-Vossman Vokman 1 29P, and let's see what we can learn about this, well, misbehaving icy object. In other more violent news, we have a tale of, well, baby stars misbehaving. Recent observations taken with the Hubble Space Telescope have looked at a series of red dwarf galaxies using ultraviolet radiation. The shade of light that is bluer than anything we can see with our human eyes, and in fact blue enough that not all of it gets to the surface of the planet. Well, this shade of light has allowed astronomers to, in surveying red dwarf stars, find, yes, they are indeed quite violent in their youth and quite dangerous to the planets that orbit them. This particular survey has the very clever acronym HAZMAT, which stands for Habitable Zones and M-Dwarf Activity Across Time. The red dwarfs that the team surveyed varied in ages, with the youngest stars being just 40 million years old. And they found that those baby stars are 100 to 1,000 times more energetic than the older stars. What this implies is that if life tried to form in the early days of one of these solar systems, it would get likely destroyed by outbursts of energy and particles coming from that red dwarf star. Now, these stars live a long time, for billions and trillions of years. So given the fullness of time, given the fact that solar systems rearrange themselves, this isn't to say that it's not possible for life to form around red dwarfs. It's just to say it's not happening early in those solar systems' history. Now, continuing our study of high energy objects and moving further in to the bluer than blue parts of the spectrum, we have a study coming to us from the Chandra X-ray Observatory, which is now up and running again, to give you an update on one of last week's stories. In this press release, we have found out that the Chandra X-ray Observatory has located the youngest pulsar ever studied to date. This not particularly poetically named object, KESS 75, is a high energy X-ray object, and it still has a nebula located around it. This is not an artist's rendition. This is an actual image of this system. This is a composite of both the X-ray and the optical light, with the blue in the center being the pulsar and the purple around it being X-ray emission coming from hot gas in the nebula that has been excited by the pulsar. The stars and material that you see all around that pulsar, that is an optical image. In studying this system, we have been able to watch how it changes since its first observations were taken back in 2000. Observations from 2000, 2006, 2009, and 2016 have been able to record how the pulsar's wind has interacted with the nebula in ways that have changed over time. This is one of those amazing instances where we're not just watching a star evolve over the full expanse of a 100-year human lifetime. We're watching it evolve over a couple of decades. This data set isn't even old enough to drink. So this amazing data set lets us see just how quickly these systems are changing. It's thought that KES 75 was formed in a supernova explosion about 500 years ago. And this is an object that is, in the scheme of the universe, not too far away. It's 19,000 light years away. And so let me reframe that by saying we would have received the light of its explosion 500 years ago. It exploded roughly 19,500 years ago, but we've only been able to observe its light for the past 500 years because of the light travel time. Telescopes are time machines. When we're looking at this object, we're looking 19,000 years back in the history of our galaxy. And now we're watching it, we're watching it evolve. Unfortunately, we don't have any records of its explosion, but we're able to infer its history from looking at the nebulosity around it and looking at how it's changing. Now, what's kind of amazing is the brightness of the pulsar's wind has been seen to decrease by 10% between 2000 and 2016, and the brightest knot in the wind's interactions with the solar nebula has decreased 30%. This is something that is going to require new and sophisticated models to understand, but as I've been highlighting all week, astronomy is an interplay between observers seeing what the universe is doing and theorists working to build computer models that explain what is observed and move beyond that to say what else we should expect to see. So here's a new challenge for all you theorists out there, and here's one new piece of the story of how pulsars evolve with time. Now, those are all the stories I have for today, and now I will be happy to take your questions. I'm realizing I don't have the chat history in front of me, so if you asked a question earlier, please repeat your question and at me in the chat. So Hanny is asking, what causes the stability of larger stars? I assume that you're asking in relationship to our story about red dwarfs being so violent. Larger stars are violent in their own way, but the amount of time that they're violent, or how they're violent, is fundamentally different. With red dwarf stars in their early years, we see massive coronal mass ejection-like activity. This is because these stars take longer to fully settle down to being able to have stable nuclear reactions in their core, to having, well, actually with them, it's their entire atmosphere is convecting. It takes them longer because they're smaller to collapse down into stable, mature stars. What we're seeing is a prolonged period of, well, their lower mass taking longer to settle into place. And as things work, as things come together, there are coronal mass ejections, there are magnetic fields that are rearranging, and all of these different activities lead to flare activity and wildly high energy emissions of radiation. You have something bigger, it collapses faster, it settles into place faster, it burns through its energy faster, it dies faster. We're just seeing a star that's going to live trillions of years. And in exchange for living much longer, it has a much longer childhood. Keeper of Maps, I appreciate that 29p sounds like an asbestos comment. I can actually go with that. Thank you, actually, Lucid. I appreciate that compliment. So Side MT is asking, is there any particular finding you're expecting from the Bepo-Colombo mission? Oh man, I'm looking forward to seeing better understandings of the inner workings of the magnetic field. There is super cool data coming from some of our solar observers that show that as Mercury orbits around the sun, it actually leaves behind a trail of particles that the material coming off of the sun have caused to be pushed off of Mercury. There's high energy particles that, as they impact Mercury, cause other particles to be released at escape velocities from the surface. These particles form a trail behind Mercury. This isn't the kind of thing that happens very often, and getting to understand the full, literal impact of the sun's magnetic fields, the sun's high energy particles, all of that on Mercury in better detail than we were able to get from the Messenger mission. This is one of those things I'm really looking forward to. And as always, high resolution images are amazing. And I look forward to seeing what new details we're able to tease out of the geophysics of Mercury from those images. Looking to see if there's any other questions out there. Anything else? It's a sleepy, rainy day here, and I just want to remind you that we're going to be back tonight with a hopefully less sleepy stream, bringing you live the Bepo-Colombo launch. Hanny is asking, do red dwarfs take a shorter time to form solar systems? No, we don't know. Solar system formation is one of those things we're still trying to figure out. Anyone who tells you they fully understand how solar systems form is lying. In general, smaller stars take longer to form. Everything just goes a little bit slower when your gravity is not quite so strong. Fenring is asking, is it possible that Mercury's core is not active, but a kind of permanent magnet, magnetized by the sun's solar wind and magnetic field? I have to admit, I just don't know. I'd have to do some research digging through the literature to answer that question. Glad to catch you, actually, Lucid. So Astrid B. London is asking, what time is the Bepo-Colombo launch? It is scheduled for 10:25 Eastern. So add 5 to that to get to London time. So that would be 3:25 London, if I'm mathing correctly. But daylight savings time is kicking in at different times in different places. Let me double check that. Sorry, while I type on stream, I want to get this correct. So I'm seeing that it's 2:30 GMT. 2:25 GMT. And we will begin our coverage half an hour earlier. Again, GMT may relate oddly. Thank you so much, Checker Kev. I'm looking for someone to say Central Eastern Time in some of the coverage. I'll be tweeting. Look for the tweets on CosmoQuest X on Twitter. We will keep you abreast of everything. So, going back to the chat. Okay, you're GMT +1. You now know exactly when you are and when the launch is. So you can expect it at 2:25. If I did the math correctly, is UTC +1 or -1? So 2:25 UTC would make it 3:25. So 3:25 London time. That works. Okay. So that's all I've got for today. Dr. Matt Richardson is waiting in the wings to take over this channel and bring you Astronomy 101. As always, this channel is a collaboration brought to you by CosmoQuest. Check out cosmoquest.org, a place where you can learn and do science. We are going to be taking next week and through November 1st off. We're working for some big changes for the channel, and it's going to take us a little time and planning to put everything together. We will continue to tweet out the news, and please come back November 1st, and we will have exciting new things to share. So don't go anywhere. We will have Matt coming to you in just a couple of minutes. As always, wherever you are in the world, have a fabulous morning, evening, or afternoon. And remember, go outside and look up. Bye-bye.